Okay. Uh, shall we? Can we start now? Still have a lot of people here to join. I think we should start. Yep, we should start. Okay. So, any questions before we start? Any questions? Any questions? Yeah. Any questions from the previous section? Hello. Can you guys hear me? Any questions from the previous section?
I am okay.
Okay.
The word is a seed
Please the rest.
with
Any
hand that I want.
questions? Okay, so if no questions, then let's continue. Okay, so in the previous section, let me bring up KeyCard. In the previous session, this is where we got to. We place our power ports, our voltage regulators. There is one voltage regulator for 7805. There is another for the 7805 is for the 5 volt regulation, and we have AMS 1117 3V3. This is for our 3V3. Now, there is a much smaller version that we could use because I think that one on Arduino can supply up to a maximum of 150 milliamps. But this one here, I think, can do about 1 amp. So technically, this is an overkill, but I'm still going to keep it anyways. Yes. We also added some capacitors. We talked about capacitors, how to use them, and I made mention that in here so far we have been using them. We have used them as what do you call it? Boosts. Oh, sorry, decoupling capacitors, right? Okay. But then there is still something, all is not well with our circuit. We still have to fix a couple of things. So we're going to look at it, the reason, and then we look at how to do the fixing. You see, so our power comes in here through the power port, and we said that according to the circuit symbol, the power port pin 1 is supposed to be the positive terminal, and pin 2 and 3 are supposed to be the negative terminal. Now, if you look at the male version, if you look at the male version of the DC barrel, which we call the DC jack, let me bring it up. Okay, so this is how a typical DC jack looks like. Okay, so the inside is normally the positive and the outside is the negative or ground. Okay, however, you realize that whatever arrangement it depends on whoever connects the wires, right? That means there is a high probability of something going wrong. That is the person connecting the negative rather to the inside and the positive to the outside. Okay, these things can happen. I think I've even been a victim of this before, so I understand what I'm saying. Okay, so in order to protect our circuit or our system against this, we have to ensure that we handle something we call reverse polarity, reverse current. Yes, reverse current. Okay. Now, the question is, how can we handle reverse current? It is simple. This means that we need to restrict current flow in our system, or yeah, in our circuit, so that it is unidirectional. What I mean by this is that we need to restrict our system such that current can only flow in one direction. Okay. Now, fortunately, there is a component for doing exactly what we need. Okay, so let's quickly look at the kind of component and what we need, how they operate. So So the component I'm talking about is the diode. So let's quickly look at just some few stuff about what a diode is, and then we come back to route our circuit. Okay. So basically, a diode gives us the ability to control current in one direction, right? So diodes serve as a lot of people like to put it, a one-way switch for current. Okay, so current can enter into it in one direction, but it can't return. That means that if we manage to put a diode on our system, then by default, we would handle reverse current. That means that even if somebody mistakenly misconnects the terminals, we are not going to have any issues with our system. Okay, so that's what we're going to look at. But before we do, it's good to know something about our diets. Okay, so current can flow in one direction. I've mentioned that, and that direction, whenever a current is flowing through, or current can flow through a diode, we say that it is forward biased. Is that okay? And that direction is what we reference as the forward direction of the current. Is that okay? Forward direction. So then the other way round is when you reverse bias, or when current cannot actually flow. Okay, that is what we call the reverse direction. And when you current cannot flow through a diode, then we say that it is reverse bias. Is that okay? So just by introducing a diode, now we have restricted the direction of current, which is a good thing. Okay. All right. Now, when in the previous session, I mentioned that when your power source is, when your energy source is an AC, right, you have to convert it to a DC, and the process is called rectification, right? We mentioned that. Now, what I didn't mention was how to achieve this rectification, okay? So the thing is that because diodes inherently have the ability to block current in one direction, by putting diodes together carefully in the way of an alternating voltage, you're able to restrict its movement and end up with a DC voltage. Now, I'm not going to go into details of that, but you can check that thing later. Okay. So, because of that, some people refer to diodes as rectifiers. Okay. So, if you see rectifier somewhere, just know that the person is probably talking about a diode. Okay. So, the diode, like every other symbol, diodes also have their own circuit symbol, and it is very simple. It is this. That's the circuit symbol. So the symbol is actually intuitive. You can see an arrow. The arrow shows the direction. The arrow shows the direction of the flow. Okay. So the positive terminal, in our previous session, we saw that positive terminal is called anode and negative terminal is called cathode. Okay, so over here, you can see that the arrow indicates the direction of flow. Now, if I try to move from the negative direction, you see that I have a block over there. So the symbol is even intuitive enough. Okay, so current can only flow from the anode to the cathode, not the other way around. Okay, and there are various configurations of diodes. They come in different forms. Okay, and these are some of the various ways you would see an actual diode. And so this is what we call this one has a metallic case. This is the stud mount. Then we have the plastic case. These guys are very common. Then this one, you see, usually for the plastic case, you see a ring. Okay, there is usually a white ring. The white ring is usually on the negative terminal. Okay, so if you pick a physical diode and you want to see how to connect it, if it is this type, just know that where the white band is, that is your negative terminal. Okay, then we also have another form of plastic case, but that one doesn't have a ring. It is rather chamfered. Okay, so there is a tapering at one of the end, and that tapering actually represents the negative terminal or the cathode. Then we have the glass ones. Usually you see Zener diodes in this form. Okay, so all these are the various configurations of diodes that you can see there. Okay, and I mean these are all through hole. I'll talk about that later. Talk about that later. Now, let's continue. So, diodes are rated according to their type, voltage, and the current capacity. Okay, remember in our previous session, I talked about some of the considerations or the things that you have to look at when you are choosing things like a capacitor. Okay, the same way I'm going to give you some of the things that you should look for when you are choosing a diode. Okay, but diodes usually you worry about their forward voltage drop, current capacity, and the type. Okay, the type I will also talk about. Now, diodes are polar. Today we are meeting the word polar and polarity very, very. I think so far this is the third time. And as I have already explained, when we say that the component is polar, it means that there is a dedicated pin for positive connection and another for negative connection. You cannot interchange them. The moment you do that, something will go wrong. Okay, so take note, diodes are polar. Diodes are polar. There is an anode or a positive terminal and a cathode or a negative terminal. Okay, let's continue. Now, we talked about forward current, reverse, and all that, right? But the question is, how do I achieve it? Okay, how can you achieve? How can you make current flow through a diode? Okay, all right. So for current to flow through a diode, first of all, we said that it has to be forward biased. So what do we mean by forward bias in a diode? It's simple. It means that connect the positive terminal to a higher potential than the negative terminal. Okay, take note of this. Connect the positive terminal to a higher potential than the negative terminal. Now, what matters is there has to be a voltage gradient or a voltage drop across the diode. Is that okay? In the forward direction. Now, it doesn't matter whatever voltage is at the negative or positive. So far as there is a voltage gradient and the direction is from positive to negative, the diode will be forward biased. So for instance, if I, let's say, connect 12 volts to my anode and 11 volts to my cathode, yes, the diode is forward biased. Okay. If I connect minus 1 volts or if I connect 0 volt to my anode and minus 3 volt to my cathode, still the diode is forward biased because 0 volt is actually higher than negative 3 volts. Okay, so it is all about having potential difference such that the voltage or the potential at the anode is higher than the potential at the cathode. Okay, that is what we mean by forward biasing uh, diode. Now, the reverse bias is the opposite. All you have to do to reverse bias a diode is to put a higher potential at the at the cathode than the anode, right? So anytime the voltage at the cathode, which is the negative terminal, is higher than that of the cathode than the anode, then the diode is reverse bias. In that case, current is theoretically not supposed to flow. However, we will see later that this is not entirely true because there is something called leakage current that still flows. However, the amount is so minute or tiny that it's easy. You can even ignore it, and everything would be okay. Right. So in reverse bias, the main condition is there is no current flow. In forward bias, there will be current flow. Okay. So that means that in our application, we have to position the diode such that if the person mistakenly connects the power terminals, the battery terminals, it will put the diode in a reverse bias mode, and that would prevent current from flowing, meaning that the circuit will not turn on at all. Okay. Now, this is better than not doing anything about this. Okay. All right. Now, one of the things that is very crucial to diodes, and because of that too, a lot of technologies have come up, is what we call the forward voltage drop. Anytime a diode is conducting, that is, if you bias it in the forward direction, okay, it actually takes some amount of the voltage that is applied across it. Now, this is what we call the forward voltage drop. Okay, forward voltage drop. So at least you need enough voltage across the diode to overcome this forward voltage drop. Now, if we go into the details of semiconductors, you realize that it's because these diodes are usually formed out of a PN junction, and there is something called the depletion region, which actually needs to be overcome in order to move current across, right? But we are not going into that. So just understand that whenever a diode is conducting, it drops some amount of voltage. So let's say if I applied 9 volts as input to the to the anode, I'm not going to get the same 9 volts at the cathode. For normal silicon signal diodes, they have a forward voltage drop between 0.6 to 0.85. Okay, so that means that depending on the current, these values may change a bit. So let's take an ideal value of 0.7. That means that if I put in 9 volts across a diode that has a forward voltage drop of 0.7, then the voltage on the cathode is going to be 8.3 volts instead of 9. This is because the diode drops some of the voltage. So you have to take note of this because it will come in handy. All right. Now, there are different types of diodes, a lot, a lot. However, uh, different types of diode and they all have different symbols. Okay, however, you realize that you still see the arrow sign in there. Okay, the arrow sign telling you the directionality of everything. Okay, so I'm not going to talk about all these things. Remember, I said that I will only touch on things that are necessary for our activity. So in this, I'm only going to talk about junction diodes and then Schottky diodes and light emitting diodes. Okay, these are the things that we'll be using in our work. So that's where I'm going to concentrate. Okay, so these are the various diode symbols. Okay, you can check them out later. So let's take light emitting diodes for instance. Now, light emitting diodes. They are just like normal diodes. However, they rather produce light when they are conducting or when they are forward biased. It's okay. So you know them. We call them LEDs all the time. We use them in a lot of stuff. You have heard of LED screens, LED bulbs, and all those kind of stuff. Is that okay? Now, the interesting thing here is that how much forward voltage it will drop depends on the color. Okay, now if you've done physics before, you understand this concept well. So there is this concept of wavelength and frequency and all those kind of stuff, right? And if you check hot energy, the amount of energy that is required, for instance, a red LED, the amount of energy required to excite it, okay, from something called the valence band to the conduction band. Sorry for the technicality. It is about 2 electron volts, okay? 2 electron volts. And it also happens that the forward voltage drop for a normal operation for normal LED, a red LED, is 2 volts. Okay, so as the color is increasing from red, so if you start from infrared diode voltage drops are usually around 1.5, 1.6, 1.8 thereabouts. Okay, then moving forward, we come to 2, which is red. Yellow or amber is about 2.1. Green is around 3 point something, I think from 2.8 to 3.2, followed by blue and white. Okay, so the spectrum, the EM spectrum actually comes with different voltage drops, and the higher you move, the larger the voltage drop. Okay, so because of this voltage drop, higher voltage drop, it makes them not ideal for doing things like voltage rectification. Because if you use them for voltage rectification, you end up dropping a lot of your voltage. Okay, so you may have to. You don't want to be losing that. Besides, nobody wants to be seeing LED flickering in a rectifier. Okay, so they are usually not ideal for voltage rectification. However, they are mostly used in circuits as display for indication. Okay, all right. So that is its symbol. Is the normal diode symbol with the two small arrows on it, showing you that there is something coming out of it. Okay, and that thing is light. Now, the next thing I want to talk about is the Schottky diode. Okay, Schottky diode. Probably if you are Britain, you may say Scotty diode or whatever. Schottky diode. Now, these diodes are very interesting in the fact that one of the things that we consider when we're choosing diodes, which is the forward voltage drop, this guy actually does a good job on it. Now, for normal silicon diodes, junction, PN junction diode, they have forward voltage drop of about zero point 0.7, but these guys have between 0.15 to 0.4. That means that if you are working with very voltage sensitive applications, you may not want all that zero point 0.7. Trust me, you may think it is nothing. But if you are working with battery powered applications, zero point 0.7 is a lot of voltage to lose. Okay. So, and another thing about Schottky diode is that they have very fast switching speed. So they are ideal for high frequency operations, and they can also handle a lot of current. In fact, so much current. Okay, so this makes these diodes very ideal, right? I think this will be the last thing. Oh, okay. Now, since we are doing a practical thing, we also have to mention about some of the things that are really important and you should look at when you are choosing diodes for your application. Now, I've mentioned a couple of things here. These are just what I see useful for what we are doing. You can read more on diodes to find out other stuff that you may have to consider. So the first one is the forward voltage drop. I've talked about that, which is how much voltage the diode drops when it is conducting. Okay, so the normal PN junction diodes will drop like 0.7, and like I said, when you are dealing with battery powered applications, this is so much and you don't want to be losing that. Okay, so you have to check. Probably you are dealing with a lithium ion battery which is only producing 3.7 volt. See, this 3.7 volts, if you are losing 0.7 of it, that is so much, because now it brings your voltage to 3 volts, which is a lot of which is an issue you have to probably consider. Okay, now the next one is the rated current. The diode you are using, because diodes are usually used as inline elements, you have to make sure that whatever diode you are using, the amount of current that the circuit requires, the diode can allow it to pass. Now, so far the Schottky diodes that I have used, they can allow 3 amps of current, which is very good. Now, you can't use something like an LED for such a thing. LEDs are allowed to operate, I think, a maximum of 20 milliamps, right? So you cannot use LEDs for this kind of application when you want to drive a large amount of current through that LED. In fact, I think I tested some time ago, and after 60 milliamps, the LED started misbehaving. So ideally, I think manufacturer's data sheet, they recommend 20 milliamps maximum. Okay, so stay with that. Then we also have what we call the maximum reverse peak voltage. Reverse peak voltage. That is how much voltage it can actually block. Okay, how much voltage. So the reverse peak voltage and maximum reverse voltage, generally talking about something similar. When you reverse bias it, how much voltage can it withstand before breaking down? Because trust me, there is actually a limit. Okay, there is actually a limit to how much voltage. So let's say if a diode is rated to have a reverse voltage block, reverse voltage of let's say 12 volts, and you connect about 15 volts to it, it's going to conduct even in the reverse region because it's going to break down. Now, when diodes break down, two things can happen. It could be due to a condition called avalanche or Zener. Okay. Now, the condition called Zener is what has been optimized to create what we call the Zener diode. Again, I'm not going to talk about those things. If you're interested, please check them out. Okay. Then when you are dealing with very fast or high frequency applications, then you would have to also reconsider the recovery time. Recovery time in simple terms is this: when the diode switches on and you switch it off, it doesn't immediately goes off. Okay, there is some lag, some latency between switch on and switch off. Okay, and that time is what we call reverse recovery. And I think it has to do with something about the junction capacitance. Again, we will not go into that details. Okay, so this reverse recovery time is important when your application is a high speed one. Okay, if you don't choose the right diode for the high speed applications, then your diode will not be ready when your system needs it to be ready or to switch on, and that could distort your signal and things may not work well. So reverse recovery time is very important when you are dealing with fast or high speed processes. Okay. Then another thing is the maximum power, which is the voltage current combination that it can handle, reverse saturation current, and the junction temperature. Okay, so junction temperature should give you a clue about what kind of application it will be used for, suitable for. I think currently I always see um, automotive grades. When you search for components, you see something like automotive grade, automotive grade. This is because they are optimized for high temperature applications. So depending on your the work you are doing, you may want to spend time to choose the right diode. Okay, but fortunately for us, our work doesn't require this much. So we are just going to use the Schottky diodes for our work. All right. So before we switch to keycard, I would take the on our web. Yes. Please, if you have any questions.
Professor, if the let us the next, how do you plug it?
I can't hear you well.
Please, 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 if the let us three legs, how do you plug it?
Oh, okay. So you are asking if the LED, so an LED with three legs. Oh, okay. So I think you could get as many as four legs for an LED. Usually they are multicolored LEDs. Okay. So the configurations usually differ. We have something called common anode or common cathode. Okay, so right now I can't tell you that connect this to that, connect this to that. It will depend on whether your LED is a common anode or common cathode. Okay, so just probably check it out, and I think usually you can identify that by the length. If you take a physical LED, the anode is always longer. The terminal for the anode is always longer than the cathode. Okay, so what I have observed about the common anode, the pin lengths are not the same. So probably just look at how yours look like and check it up on Google. If I give you an answer here, it may backfire because there are different configurations for that. Please, is it okay? For instance,
Yes,
an
yes,
LED with
yes,
three
yes, thank
pins
you.
could be bicolor. It could have two colors. So the two pins will be dedicated for switching the individual colors, and they all have a common ground. That will be the third pin. So just check it up on the internet. Okay, if it is a common anode, you may have to connect it different way. If it's a common cathode, you have to different. Yeah. Any other questions, please?
Uh, a quick one. You said that ladder is used as a one-way switch, like it can.
I can't really hear you well. If you could adjust your audio a bit.
Okay.
Yeah.
Um, my question is, you can hear me now very well.
Yes, please. Yeah, I can.
Okay. The diodes are used as a one-way switch,
Yeah.
like they can block uh, current. They can allow current in one way.
Yes.
So can you say that that is the case for also the leg? Because most of the times they're used for indication purposes. So can you say that the same many LEDs also can be used for uh, to direct current to one way?
Actually, yes. LEDs are diodes. The only difference is that they produce lights when they are conducting. So if you connect an LED in a circuit, you have actually connected a diode. Everything a diode can do, LED will do the same thing. It will also allow current to pass one way, not the other way around. I don't know if I got your question clearly, but what I heard is, are you okay with it?
Yeah,
Uh,
it's fine.
Okay, okay. Uh, Please take note, LEDs are also diodes, okay? So when you connect an LED in a circuit, you have connected a diode in a circuit. God willing, tomorrow I will do a small simulation on the behavior of LEDs in circuit. They are very interesting, okay? Very interesting. The way they affect circuits, I'll do a small simulation to explain the concept. Then we'll continue. Yeah, please, any other question? Any other question?
Please, what is the function of diode?
Oh, okay. So we said anytime we want current to move in just one direction, okay? So we want current to move one way but not to return through that same direction. We put an LED to do that. Sorry, a diode to do that.
It's okay, thank you.
Yeah. Please, any other questions? Any other questions? All right. So if there is no question, then let's quickly go back to our circuits and then put in diodes. Now that we know how to use them, we can introduce them into our circuit. So give me a moment to switch. Okay, a hand is up. Please, you can go ahead and ask a question.
Okay, I'm asking, is it possible to connect more than one diode, maybe in series or in parallel, instead of just one?
Oh,
Let's
yes,
say like,
go on,
is
go
it
on.
possible?
Yes,
Is it
I'm
possible?
going to show you something very soon, okay?
Okay,
Uh, to explain what you are asking, I did something
okay,
I want to show you. Okay, I don't have that here. I don't have that here, but I can still show you here. So let's say if you take something like a GSM module, right?
yes,
GSM, let's say SIM 800. SIM 800 actually operates on SIM 800 operates on 4.2 volts between 3.8 to 4.2 volt. I think no, it's between 4 volts to 4.4 volts. Is that okay? Good.
okay,
So
Okay.
if you are working with a 5-volt power source, for instance, and you want to give the same 800 the voltage it needs 4.2 or let's say 4.1, right, without putting
It's
in any voltage regulator. You could
3.7 to
What I
4.4 volts.
do is
yes,
connect three Schottky diodes in series, right,
yes,
and each diode will take about zero point 0.3, so three in series will add up to 0.9. So zero point 0.9 from 5 volts now gives me 4.1,
yes,
and that solves my problem. So yes, you can serialize LED diodes, you can connect them in parallel. So far as they serve the purpose that you intend to, you can do that.
okay,
Yes.
okay, thank you.
Okay. All right. So how do we prevent reverse current, reverse polarity, reverse current? How do we prevent that? Fortunately, this is our input voltage. Our incoming voltage is the VCC, right? And we need to protect the rest of the circuit. That means it has to come, we have to place the diode before the rest of the circuit. That's what we have to do. So I'm going to adjust this. I'm going to please turn off your mic for us. Thank you. I'm going to adjust this. Okay, so I'm going to put my LED here. Sorry, my diode here. And this is the point where you have to think about what type of diode to choose. Remember, I said one of the important things would be the forward voltage drop and the amount of current that it can handle, and also the reverse voltage. Okay, so let's go online. There is a particular LED I want to use, so I'm going to Google it for you to see. It is a Schottky diode. So I think 1N58, 20 or 18 thereabout. Okay, let's
Okay.
check this guy out. Okay, so it's produced by on semi. Let's check its data sheet, and please develop an attitude of checking data sheet. Okay, so quickly over here we know that this is a Schottky barrier rectifier. That is good. So extremely low VF stands for forward voltage drop. Okay, low power loss, that is high efficiency. That is also good for what we are trying to do. We don't care about this, don't care about that, we don't care about that. But when we come here, 3 amps of current, which is actually good because the system we are building, we don't even anticipate drawing or driving about 1 amp. Okay, technically the Arduino should consume less than 500 unless you interface some circuit that requires so much. Okay, but that too, I'll show you how not to do that. Okay, and it can actually, I think it can withstand 20, 30, and 40 volts. Now, let's not even stay here. Let's go to electrical characteristics. I think I've passed it. Okay, so you can see that there are different varieties of it. Okay, there are different varieties and they come in different packages. You can check these things out, but that's not my okay. So electrical characteristics. So maximum instantaneous forward voltage. So you see for the 5820, these are the forward voltages. Now look at this. When the forward current is 1 amp, it is dropping about zero point 0.3. At 3 amps, it is dropping about zero point 0.4, which is actually very good. Okay, because for application, we are never even hitting 3 amps anyways. Okay, so I'm going to choose that Schottky diode as the diode for our reverse current protection. Now let's place it. We go to components. Uh, okay, and we search for D. So in KiCad, D is D Schottky. Okay, D Schottky. And I think there should be a smaller version. Usually I like working, yeah. So D Schottky small. I'll pick this, press on R to rotate it, and place it in there. Now take note. You see, when I place it in here, I don't have any uh, joints like this happening. Is that okay? If that happened, it will mean that my connection wasn't right and the diode is actually overlapping. That means I have created a short circuit. Okay, so always please make sure the connection is as you intended. Now we are going to use 1N uh, 5820. I'm going to use that version, so we put it on it. Okay, and then day 20. Okay, now there is something, probably let me show you right now how to do that. Okay, let me show you right now. You see, when you are developing, and let's say you are working for a company, then chances are that you would have to order for the printing or the send an invoice to, we call it the bill of material, to some company somewhere to source your components, right? That means you need to provide them with the right values, data sheets, and all those kind of stuff. Now, what I usually do, for instance, 780405, if I want to put information on it, I'll go to DigiKey Electronics. Okay, DigiKey Electronics, and make a search for the component that I'm looking for. They have a very good database of almost anything that you need. So I'll put in, let's say AMS 1117.3.3, right? And do I have it showing? Okay, let's choose this one and see. AMS. Okay, I'm not getting AMS. It's obsolete, not this. Okay, 7805. Yeah, I think we have something. Oh, what is this? All right, I'm coming. Okay, So let me LM7805. Okay, so something like this. Yes. So let's assume this is what we are going with. Okay, this is not the package we'll be using anyway. Okay, so if you select the particular component, they should have. Okay, so let me come here. Yeah, so let's choose this one for instance. Okay, so you see, DigiKey gives you a lot of information about that component, right? So what you can do is copy this information and assign it to your component. So for instance, manufacturer is Texas Instrument. I'll pick it. Then on the component, press on E to edit, then you see you can add your fields. So I can add manufacturer. Now this is very important if you be asking a supplier to deliver this thing for you. Okay, they will need this information. The component value. So again, let's go to DigiKey. This is the digi key part number. That's not what we want. So this is the manufacturer product number. You can grab that one too and add it. Product number. Okay. Product number, and then put it in there. Then so let's add a couple of information. So description, copy, and then paste. I think this is okay. So add description. Okay, so KeyCard allows you to do all this on the component. Is that okay? So let's say that's all I need. You save it. Now, when you generate something called the bill of material, this information will be available, and it makes it easy for your supplier to identify the component for you. Okay. All right. So by inserting, now we've inserted this Schottky diode over here. That means we are good. We are good. There is one more thing we need. We right now what we are doing is protecting our circuit, okay, from the power side. There is one more thing that we want to. This diode would only guard against reverse current, right? Reverse current. But there could also be an instance where something may short circuit our Arduino. Maybe, under the Arduino, you have the terminals and some pins showing, right? Assuming somebody mistakenly places the Arduino on a metallic surface, a lot will go wrong. Okay? Now, one of the things that is likely to happen is what we call short circuit. Short circuit can happen. And we want to prevent short circuit. Now, short circuit is just a condition where a very large amount of current flows through your circuit because of a breach, a direct connection between the positive terminal and the negative terminal. Okay, when you connect them directly, you will create what we call a short circuit. And trust me, if your power source can deliver enough current, it can draw so much current until something bends to break the connection. Okay, so let's guard against that. So what we will do is to introduce a fuse, and actually, if you look on Arduino, there is a fuse on it, which is supposed to protect your board from short circuit. So we're going to do the same thing. Now, what the fuse does is it has a rating. So let's say if the fuse is rated 500 milliamps, then anytime more than that amount of current is flowing, it will break. The fuse will break. It's just like the normal fuse we have in our homes, on our electrical appliances and stuff. But then we don't also want a situation where every time we have that situation, we will have to desolder and replace the fuse. So fortunately in electronics, there is another type of fuse that we call polyresettable fuse, okay, or resettable fuse. They can break all right, but once the short circuit condition is eliminated, they can recover, okay. So those are the kind of fuses that we want. So let's go ahead and place that kind of fuse. So come in here, place that, and look for polyfuse. Okay, that's the name. I'll look for the small version. Again, this is the symbol for a fuse. And here we're going to use 1 amp. Okay, we're going to use 1 amp fuse in it. So let me just put 1 amp over here. Okay, so take note of the polyfuse. A normal fuse is the symbol for a normal fuse is without this crossing bar, okay? The polyfuse has this because of its ability to recover itself. So now we've gathered, this diode is guarding our system from reverse polarity, and then this is protecting against short circuit. Is that okay? So I think we are good on the power side. Now, one last thing to do at the power side before we call it a day, or we call it done, sorry, is to how do we know that our system has power? Okay, how do we know that our system has power? We need something to give us a clue. Fortunately, we just talked about light emitting diodes, and we said that they are usually used for what? Indications. Okay, so I'm going to bring in a light emitting diode, and I'm going to use the color red, the red color. Oh, sorry, you can't search by color. So LED small. Okay, so technically I could, if I let me just connect it over here. Okay, and let me give it a value of red. So this is going to be, or let me call it power. Okay, this will give an indication that there is power in our system. And of course, we need to connect it up. So I'll link it to the ground over here. Link it to the ground over here. And which of the power sources do I want to sense? It makes sense to sense on the 5 volts, right? Because if your VCC comes in, then it means that your 5-volt regulator is going to generate the 5-volt output. So by putting this on the 5-volt signal, I will be able to know that the VCC is there and my voltage regulator is also working. Well, you can also choose to put it on the 3.3 volts so that by it turning on, you could know that everything else is working. But I'm just going to leave it on the 5 volts. However, there is a little problem. Okay, the problem is that since you're going to use a red LED here, the forward voltage for a red LED is about 2.1 volts. Okay, that means that if we put this voltage there, then remember our first session, sometimes the energy source is more than the load requires, sometimes the energy source is less, sometimes it is equal. Unfortunately, it is not equal, it is more. So the question is, how do we deal with the excess voltage? Because we only need 2 volts here, and in fact this 2 volt that we need, we also don't want the LED to be very bright. So you're going to drive only a current of, allow only a current of 10 milliamps through it, right? So with a current of 10 milliamps and a voltage of 2 volts, then we will have 3 volts to deal with. The question is, how do we deal with these 3 volts? This is when another type of component called the resistors come in. Fortunately, the session where I talk in depth about resistors is tomorrow. So I'm still going to use resistors anyways. But then, God willing, tomorrow I'll talk about the very important things that you need to know when selecting resistors. Okay, so let's go ahead, bring in a resistor. So a resistor, basically in circuits, okay, primarily has the ability to divide voltage. Okay, usually this is how I like to think about it. Instead of thinking about current, a resistor has the ability to divide voltage and even divide current. Okay, so if it has the ability to divide voltage, then it means that if I put some resistor here and choose the right value, then this 5 volts is going to be split between this and that. But right now, I already know how much voltage I need across this red, right? That would be 2 volts. Let's do some calculation. Let's do just a little calculation so that tomorrow, God willing, I'm going to talk much about resistors. So I'm gonna bring up, let me bring up Microsoft Paint. Yeah, if you have any question as I'm setting up, you could ask, please. If you are texting me, I'm actually not looking at the chat. Okay, I have just two screens and they are already full. So, all right, your hands is up. Your question.
Okay, thank you. Can you hear me?
Yes, please.
Okay. Um, the question I wanted to ask is that in your power supply, aren't you using any power supply filtering?
What do you mean by power supply filtering?
So maybe filtering the power supply from, let's say, um, high frequency spikes. No, I've seen in some designs whereby um, they use ferrite beads in the power supply filtering. Sometimes maybe 100 ohm at 100 kilohertz frequency, like things like that.
Okay, so
So maybe
you
you
remember
can say something about that.
you remember the values you are mentioning, right? We fortunately don't have any of those in what we are doing. Okay, our power is coming from the DC source, and we are trusting the DC source to do that job for us. Now, what we are in any ways checking is some light filtering. So if you look on the barrel, you can see that there is this small capacitor over here. Now, about ferrite beads, personally, I don't like to use ferrite beads in my work. Okay, because what I've realized is that if you are able to properly lay out your boards, you don't actually need ferrite beads. Seriously, you don't actually need them. If you do a good job with your board laying out and stuff, you don't really need them. So personally, I haven't even used any ferrite beads in any work that I've done before. Okay. Yeah. So we are trusting right now. We are trusting our system is able to the source is somewhat clean. Okay, it's clean DC, and we don't have to worry about many things from there. Is that okay? All right. Yeah. Ahmed, I think your hand is up. If you have any
So,
question, I'm trying to.
Prof,
Yeah. Yes, sir.
follow up on the ferrite bits. So,
Okay.
what if, let's say, for signal, like you are getting the signal, can you use it like in place of power? Because I've been using it for my signal processing stuff.
Yeah. Okay. So usually, I think the ferrite beads, the way it operates is when we have transient, its properties, its resistance or something varies with varying
Electromagnetic,
voltage and exactly,
electromagnetic noise and all that.
exactly. Okay, but you see, all these things can be avoided through proper PCB management, PCB route management. Okay, don't worry. When we get to the PCB design session, I'll talk about some of these things. Okay,
Okay,
so
Prof.
usually when I pick any, let's say I'm working with an IC and there is, I take the application notes and I have some ferrite bits in there. Usually I strip them off, I take them off, and just ensure proper PCB design. That's all.
Okay, Prof. I wanted to ask again. Normally, when me, like, let's say me personally, when I'm doing the power supply, I put a capacitor for the input and then the output.
Okay.
Is it a waste for putting it in the
No,
for
no,
both
no,
the
it's
input
not
and the output?
actually a waste. Actually, if you look at the data sheet for this component, you realize that there is a capacitor at the input and a capacitor at the output. Okay,
Okay,
there
okay,
is, yeah. And usually, if they use, let's say, 100 microfarad here, they'll use a 10 microfarad over there. That has been something like what I've seen people do. Is that okay? But of course, you see, this is my VCC, and I have 100 microfarad here. So that is technically going to the input, but I'm using this guy as the overall board capacitor. Okay, so that's why I didn't attach it to this guy, but it is still linked to this VCC. And on the output of the 5 volts, I have another 100 microfarad there. Okay, so when you use them, yes, you need to put capacitors there. Yes, please. Any other questions? Any other questions?
Uncle, please, are you using any diode for the circuit?
Any,
Diode,
I said, am I using any diode for the circuit?
please, yes.
Yes, so we have this. This is a diode, 1N5820. Okay, it's a Schottky diode. Okay, and
Uncle,
also,
please,
come
please,
again.
please, asking, like, you don't look at the number, you just take any diode and put it there.
No, why did you go off? Because in choosing this, I quite explained so much about the reason we chose this, right? Were
Okay,
you
okay.
off? So you don't just choose, okay? You don't just choose. There are conditions, like the
But
fault
the
voltage drop, how
network.
much current you are dealing with, all these things. You have to look at it, okay? So you don't just take any diode and put it there. Are you okay?
Please, thank you.
All
Please,
right.
yes, thank you.
Sir,
Yeah, please. Any more questions? Keep them coming. Keep them coming.
Yeah, Prof.
sir,
Yes, sir.
Yeah, when connecting the diode, you mentioned
Uh-huh.
that the connection might be wrong. Are we to expect some nodes indicating that it's connected to other circuits or what, other components or what?
I didn't get you well.
So when connecting the diode, when you
Yeah.
place the diode, you say
Uh-huh.
sometimes you might see it this way as if it's connected, but then it's not.
Oh, yes, 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 yes.
Yeah.
I don't know
So
if I can. I don't know if I can. Okay, so let me see if I can do what I was talking about. So let's say, when I was connecting the diode, the line was like this, and I dropped the diode on it, right?
yeah,
So assuming, I'm just trying to. Okay, it's not doable. So there are some circuit designers. When I drop this like this, it won't break the line and insert the diode. It will just overlay it. Do you
oh,
get the point?
okay,
It will just
yeah, I
overlay,
get
but
it.
you can see that key card is dragging along with the wires because it didn't overlay. It splitted the net and inserted it in there.
Yeah,
Is
I
that
get
okay?
it.
Uh-huh.
All right.
So if that situation happens, then you are going to have something like this. It will be like you have your diode and you have bypassed it. Because if you are routing the PCB, this connection will mean that bypass this diode. That means, in essence, the diode would be there doing nothing. Okay, that's why I said always be careful when you are putting these things. Okay, if you don't expect to see this round dot shows that more than two connections are at that place. Okay, so anytime you see them, we call them junctions. Anytime you see a junction and you are not expecting a junction, please pay attention to it. Okay, all right.
Okay.
Please, any other question?
Prof, please,
hello, sir.
so, someone told me you use the capacitor. We have a one called fixed capacitor, but in the capacitor you show that it didn't show any fixed capacitor.
We call what?
Fixing capacitor. Someone told me that the capacitor, they have some called fixing capacitor, but in the
Fixing
capacitor you show
capacitor.
that there isn't any.
Wait, did you say
Please, yes.
fixed capacitor?
Please, no, fixing.
Fixing.
Please, yes.
I seriously haven't heard of fixing capacitor. What I think you may be talking about is fixed and variable capacitors. Okay, so if that is the
Please, okay.
situation, a fixed capacitor is a capacitor whose values cannot be changed. There are some capacitors, what in radios we use to change the frequency. If you want to change the radio frequency, the thing that you use to adjust is a type of capacitor, but it's called a variable capacitor. Okay,
Please,
so
okay. Please, okay.
yeah, so if the capacitor's value can be adjusted by some means, then we call it a variable capacitor. But it is not like a particular type of capacitor, it's just a classification of capacitor. Okay,
Please, okay. Thanks.
all right. Please, any other question? Joel Adu, your hands is up. Please, any other question? Any other question?
Prof,
Elvis.
please, I'd like to know why you used one amp as at the fuse.
Okay, okay,
Why exactly one amp? Why not
okay,
any other version than one amp?
okay. So actually, if you look at the Arduino documentation, right? Uh, I think Arduino maximum will be like 600 milliamps. Okay, but then usually, okay, let's do some calculation. How many digital pins do we have on the Arduino? We have about 20, right? You have about 20. Now, ideally, each of the digital pin can supply 20 milliamps, but to some extent, you can draw about 40 from them, which is not ideal. Okay, so let's say you have connected all your pins, and 20 of the pins, and then you are drawing 20 milliamps from all of them. So 20 times 20 milliamps, that would be 400 milliamps total, right? Right? That is like the total amount of current the Arduino board can deliver to external systems. Now, the microcontroller itself is a pico power. It doesn't draw that much, but let's even give the microcontroller 50 milliamps. That gives us a total of about 400, right? Let's give the rest of the components, the other stuff. Let's give all of them even 100. That will give us a total of 550. Okay, so technically the Arduino board itself is not supposed to pull so much current. Please, are you getting it? So one amp is actually good. Now, the only time you can draw so much will be probably if you are tapping power from the 5 volt directly, or the 12 volt, the 5 volts, the 12 volt, or the 3 volt directly to some system that is power hungry. But in that case, you will not. It is not coming to the Arduino. It is going to that particular power, that particular system, right? So the Arduino is actually good with 500 milliamp, top 600 milliamps. Please, are you okay with it? Hello? Hello, Joel.
Yeah, I'm okay. I also like to find out. You said you have the fuse, you have the reset fuse,
Yeah, poly resettable fuse.
fully resettable fuse. How does it work?
It's
Is
just
it
normal.
a
It's just
switch
normal
pattern?
fuse, but when the let's for instance, if we insert a poly resettable fuse of 1 amp, right? When it has the triggering voltage where it will break down, like a normal fuse has broken down, and it will remain in the breakdown state until the short circuit condition is actually over. Then it will recover back as if nothing happened.
Oh, okay.
Yeah, it's like a tripper. What do you call it? Um, Electrical guys have this circuit breaker, right? Just that this one is automatic. You don't have to go and put it online. Okay, it does it by itself. It recovers by itself. All right. Please, one last question, then we continue. One last question, then we continue.
Uncle, please, why did you use only one fuse for the settings?
That's all we need. Okay, we don't need multiple fields. We need just one.
Okay, okay, okay.
All right. Okay, so quickly, I'm going to share something. Let's find out. Let's do some working out. Let's work some things out. Have to do some switching again. Okay, just a moment, please. Mm, just a moment. Okay. Uh, so share. I want us to look at what value of resistor to choose, and then to continue. Okay, all right. So the situation at hand right now. Please, can you all see my Paint software? Okay, so we have 5 votes, and we want to power an LED. Okay, we want to power an LED. Now, this LED we know will drop 2 volts on forward on conduction, right? And we actually want to restrict, though the LED could allow 20 milliamps of current to flow, we want to restrict the current to just 10 milliamps because we don't want it to be too bright, right? Okay, so that means that we will be drawing a current of 10 milliamps from this 5 volt power source. Is that okay? But then if we drop 2 volts across the LED, we would have an excess of 3 volts, and that 3 volts is what we need this resistor to handle. Is that okay? Now, since these two are in series, that means the same 10 milliamps of current is going to flow through this. Now, tomorrow, for those who don't know, we are going to talk about Ohm's law. And Ohm's law is simply this. It says that whenever current flows through any conductor, okay, there is a reaction that leads to generation of voltage across that conductor, and that voltage is directly proportional to the resistance of that conductor and the current flowing through it. So we can mathematically express it as the voltage drop, okay, the voltage drop across. Take note, voltage always drops across something. So let's say this is the voltage we are looking at, something dropping across this resistor will be equal to the current flowing through it and the resistance. Okay. Now, fortunately, we know what voltage should drop. That is our 3 volts. And we know how much current we want to pass. That is 10 milliamps, right? So what we don't know is the resistance that we should choose. So from maths, we make R the subject. We get the resistance to be equal to 3 divided by 10 milliamps, which will give us, I think, what would that be? Milli will go up and become a K, so I think 3K, right? Please confirm this for me. Do we get 3K? No, 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 no. 3K, no, 10. So 10 shifted, that's 0.3 times K. So no, no, no. So that would be 0.3K, so that would be 300, right? 300 ohms, right? 300 ohms. So it means that we need a resistor of 300 ohms. Now, you don't choose a resistor only based on its resistance, okay? There are other things that you have to consider. Every resistors come in different sizes. You can have a 300 ohm that is big, a 300 ohm that is small, in that order, right? Now, the sizes of resistors are associated with their power. The power here is the ability to dissipate the excess energy they are supposed to handle. Is that okay? Now, in the first session, I talked about power being the work done on the electrons as they are moved through the circuit, right? So we said that it's voltage times what? Times current, okay? Now take note, this voltage here is not the voltage of the source. It is the voltage that is dropping across that component, which in this case is going to be 3 volts. And the current flowing, which because the components are in series, the same 10 milliamps will flow through them, right? So when we do this, we are going to get we're going to get 30 milliwatts. Okay, 30 milliwatt. Power is in watts, and since we have milli here, 30 milliwatt, that means that's about 0.03 watts, right? Good. Now, if you go to town to buy resistors, you will get, I think there is a 1/16 watt or something. I will have to, but we have 1/8 watts, okay, one quarter or a quarter watts. We have half watts, we have 1 watt, we have 2 watts, and so on. Is that okay? Now, if you check this value, it is not even closer to 1/16. True or false? If we divide 1 by 16, do you get this? Can somebody confirm? What do you get? 1 divided by 60. Yes, the mathematicians. Hello, guys. Are you there? 0.06, right? 0.06. 0.0625. Okay. So you see, 0.0625 is still bigger than 0.03, true of us. So that means you can conveniently choose this resistor, this wattage, if it exists. However, my rule of thumb is usually to choose twice the required wattage. That's what I do in my circuit. So twice this is probably going to be just 0.06, but I'll still go for 1/8 watt, or better still, just go for 1/4 watts. Okay, so these are some of the things that you should look at when you are choosing a resistor. Okay, not just the resistance, but also the wattage, because the wattage also determines the size, how big the resistor is. Okay, any questions? So we know that we need a 300 ohm resistor. However, there is one more parameter you need to know. There are standard resistors on the market, so there are certain values you may not get, or there are certain values you may not get at certain tolerance values. Resistors also come in different tolerance. When in the morning we saw that capacitors do have tolerance, and I said that the tolerance has to do with how much error in the value reading that you can get, right? Resistors, I think you can get 1% tolerance, 5%, 10%, and I think 20%, right? Now, depending on the tolerance value, there's certain values are not available, but I know 300 ohm would be available for one ohm, but I don't know for the rest, so maybe you could check later, okay? All right, so 300 ohm is actually a standard resistor that we can get on the market. So let's go back to our circuit and continue. I'll talk more about resistors tomorrow. Okay. Please, any questions? Please, any questions? Any questions?
I do have a question.
Okay.
Um, isn't 10 milliamps too much for this indicator LED?
No, please. It's a matter of choice. If you want 5 milliamps, you can just set it that. Okay. It doesn't change anything. Yeah.
Because I seen some designs that some people put in 5.1K, others 1K, others
Now, if you put a
1.5K.
5.1K on an LED path based on 5 volts, you are basically probably telling it to flow, have just 1 milliamp flowing. Maybe they use 5 volt, but not on the they use 5.1K, but not on the on the 5 volt line. If you put 5K on the 5 volt line, calculate the current and see. That's too small.
Some people put it on a 3.3 volts. I recently watched
Well,
a tutorial
the
video
whole thing is
on a
LED
3.3
is
and then
about powering up, and LED is about brightness. If that gives them the brightness they need, then why not? Do you get the point here? Using an LED is about the brightness you need. I could decide to make 20 milliamps flow through it. It is just the brightness. So if for my application I just need it to be very dim, then whatever resistor value suits it, you can just use it. Personally, when I'm doing this things, I throw in 1K and do that. But I just wanted people to know how to find out the values for this. So it's about how much current you want to flow. It's not like there is a standard that when you are dealing with LEDs, put this. No, it's about how much current you want to flow. That's all. Are you okay with that?
okay.
Yeah.
A follow-up question on that.
Okay.
So what is the intended voltage supply for your system?
It's any DC voltage from the voltage regulator we are using could handle up to 35 volts, but it's not ideal to drive it that. So any voltage from 7 volts up to 18 volts is okay. Even 24 volts is okay.
Okay, and then the amperage. I see you put in a 1 amp fuse, polyfuse.
Yep.
So are you restricting um it to only 1 amp maximum current?
Yep. You see, the way current works, okay, current is always a reaction to voltage. Know that you don't force current into a system. The system determines what current it needs. You can only set the voltage the system needs and it will handle its own current. Okay? Now, I just made an analysis. Even if you draw 20 milliamps from all the Arduino pins, the digital pins, that will be a total of 400 milliamps. The IC itself operates below 50 milliamps. Okay, now even if we give the rest of the components on the board 100 milliamps, that will still be a total of about 550. So tops, even if we rate our Arduino at 600 milliamps, it is still workable. You see, the mistake people do is trying to source so much power from the Arduino's 5 volts pin. But the Arduino board itself doesn't require that much of current. Is that okay for you?
Well, I do get that. Yes, I understand that, but
Okay.
then I'm seeing me seeing the 1 amp polyfuse over there. Like to me, intuitively, it tells me that okay, the system is being limited to, let's say, the maximum current it can, let's say, sustain is, let's
No,
say, 1 amp or
system I'm
something. Just
designing
in
wouldn't.
case of
Okay. Hello.
let's say short circuits, in case of a short circuit,
Mm-hmm.
the polyfuse is there to protect, and then once it exceeds 1 amp, it or it blows up or something. I don't know, but if
I
that is what is intended.
I'm not actually even getting what you mean. So listen, this is what we are doing here. Okay. This board we are designing will not even inherently pull more than 600 milliamps. This polyfuse is just there in the case of a short circuit. And just to be very fair, I'm limiting that to 1 amp. If in your application you think your system wouldn't even get to 300 milliamps, you see, there is no generic system. You are always designing for what's your load intent. So there shouldn't be like, oh, I saw this here, I saw that here. You don't know what the person intended to do. That's number one. Okay, I could raise this polyfuse to, let's say, 1.5 amps, because of course this LM7805 can allow a maximum of 1.5 amps. I could do that. But you see, the whole thing is about intended purpose. What we are doing, we don't need that much current. So as a designer, I have to restrict it. If somebody else is doing this, and yes, probably they are using a 5 volt regulator that could probably drive 3 amps, and you see a 3 amp over there, it's because it serves their purpose. It's not because, generally speaking, anytime you are doing this, you should use 3 amps regulator. So understand these things. Your circuit is up to you to design. You design according to your needs, not according to what somebody else is saying. Is it okay?
Okay, can you hear me now?
Yeah, I can hear you.
Okay, yeah. So I understand all that you said, but I just wanted to know that the polyfuse you place over there with a 1 amp value. Are you
Mm-hmm.
trying to say that, or the intended purpose is that to restrict the system to a maximum of one current,
It's not
1 amp?
restricting. It's not okay.
Is that
Yes.
it?
So in actual sense, it will restrict the system if it draws more than 1 amp. But then, like I said, this system does not even intend to go. The intention of the system won't even make it go beyond that. Okay. So this polyfuse main purpose here is to prevent short circuit, to uh, regulate short circuit current. The system is not even getting to 800. And if it does, yes, I want the polyfuse to trip. It's just that. But one thing I get confusing from your side, and I want you to understand is that when you are designing a circuit, it is not about you saw somebody doing something. You don't know why the person did it. You should always design based on your requirement. If this system, I needed to even trip the polyfuse at 300 milliamps, that is what I want. That's what I have to put there. It's not about you saw this and I saw, no, what is your circuit demanded? Okay, that is how you design your stuff. That is the understanding I need you to get. So that some of these things you don't worry yourself about. Okay, somebody was using a 3K, there is always an intended purpose. And trust me, there are a lot of people online, there are a lot of circuits online, they have no idea what they are doing. The the fact that you are seeing something online doesn't mean it is the standard. Okay, so what I'm trying to get is that these things you design them according to your need, according to your need. That's why you need to understand these fundamentals. Okay. Hello, can you hear me? All right, please, any other question? Okay.
Yeah, yeah, that's fine. That's fine.
So the next thing we're going to do right now, we know that if we want a voltage of a current of if we want a current of 10 milliamps to flow through this, then the resistor value that we have to use is 300, right? So yes, for now, let's just drop it in. So I'm going to bring up a resistor. To set for resistor, you go to R, okay, but this time I need a small version. And then unfortunately it won't fit. So let's do some adjustments. Oops, I have to sacrifice this. Okay, so let's put a 300R. Now, usually resistors are actually measured in ohms, okay? But mostly in electronics, you see their prefixes. For instance, if I have 3000 ohms, I would rather prefer to write 3K. If I have 10,000 ohms, I would prefer to write 10K in that order. So you see K for kilo, M for mega, G for giga. Is that okay? In a situation where your resistance is below, if the resistance is below 1,000, then we usually put R on them. Is that okay? We usually put an R because actually the ohm symbol is not a standard keyboard symbol, so we usually put an R over there. So take note of that. Okay, but you see, the thing is, in actual sense, if I'm building out this circuit, this is just a power indicator. I don't need it to be very bright, right? If I throw in a 1K here, it will still do the work. But the thing is, what do you want to do? So far as you understand how to do that, that is all that matters. Okay, so please get these things right. Okay, so I think we are good on our power right now. We are good on our power right now. Let's check. Let's cross check. We have our inputs. We have something to deal with high frequency stuff. We have a diode here to prevent reverse current. We have a fuse here to prevent short circuits. We have a 5-volt regulator, 3-volt regulator. We have capacitors here to smoothen out or to serve as decoupling capacitors for our board. Then we have an indicator to show us that yes, of course, power is on the board. Okay. When second and start at 2:30, 3:30, 4 o'clock. Anna, when is it ending? 1:30, 2:30, 3:30, 4:30. Oh, we still have more time. Okay, so let me check next on the list what we have to do. Any questions? Any questions? Do you have any questions coming? Okay. Please, do you have any questions? Let's see. I think this session has been very
Sir,
fast.
so
Yes,
please,
sir.
are we doing a switch mode power supply?
No, 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 please. We are not using switch mode. It's just a linear regulator.
Oh, okay.
Yeah.
Thank you, sir.
However, the power supply you may use could come from a switch mode power supply or, uh, I mean, a battery, whatever. So far as it's a DC source, yes. Yeah, please let's take some questions. Let's take some questions. I think uh, I overestimated the time for this particular session. I overestimated the time. Okay, but I think we could probably match lesson three. Lesson three, protective resistor. Okay, good. So usually in circuit terms, you will hear people calling this protective resistor. Okay, and actually, yes, that is the job it does. It is here so that it protects this LED from overvoltage. Is that okay? Now, the way LEDs actually work in circuit is very interesting. You see, this LED has to allow current to pass before there can be conduction. Okay, so when you put an LED and a resistor in series, unlike like two resistors that will start sharing the voltage right away, that doesn't happen. What will happen is that the LED voltage, if I keep increasing, let's say I start changing this voltage from ground to 5 volt, what is going to happen is that the voltage, the majority of the voltage will start building up across the LED. Okay, you almost not see. Let me see if I have any simulator and check, demonstrate that. Multisim. Oops, I haven't installed it. Proteus. Not installed. Okay, probably I'll do that. But let me come back to the explanation. When you change this, let's say I change this to, let's say, 1 volt and increase it from there, 1 volt, 2 volt, 3 volt, in that order, you realize that before the LED completely turns on, majority of the voltage will be dropping across the LED, not across the resistor. Okay, until the LED's voltage saturate, that is when you see that any increased voltage actively drops across the resistor instead of the LED. And it is a very interesting thing to see. Okay, so that is the reason we call this thing a protective resistor. Because the moment the LED takes its source, any excess voltages, yes, the LED might change a little, but it is not as much as will drop across the resistor. Okay. All right. Please, any questions? Let's take some questions and then we continue. Probably I'll have to do a second portion of the third session here because we are done with the second session. We are actually done with the second session. I thought it would take a lot of time, but it didn't. Yes. Any questions? Any questions? Any questions, please? We are done with the voltage for our board. The next thing that we're going to do is voltage selection. Now, if you look at an Arduino, you can power an Arduino using the USB port or using the DC barrel, right? And the Arduino actually has something, a voltage selection mechanism that it uses. I'm going to show you the two ways we can actually do that. Then I'll select one for the board, but then for your information, when you are doing your own thing and you happen to need such a function, you can implement which of them that you want. Okay, so the next session that we're going to do, we brought the power in here. We have 5 volt, but there is also another thing that could supply power to our system, and that is the USB port. The USB port. So if no question, then let's quickly look at that. Let's go and bring the USB ports to our system. Now, the USB ports Arduino uses, I've forgotten the name. Is it type B? I think it's type B or something. Let's just check online. Arduino USB ports. Arduino has really target name on a lot of things. I think it's type B or something. Okay. Check out on images. So the USB port that we are looking at is this one that it mostly comes with printers. Let me just check USB ports. Okay, and the types. Yeah, type. I think this should be type B. Should be type B. Type B. Type B. Okay, so you have type B. Good. So that the Arduino Uno board uses the type B USB port. Okay, so let's note that. Now let's go to keycard and pick up that. So over here, we can choose from the connect the power the component sources and look for USB. Okay, underscore B. Okay, this is very, very important. Okay, but there are different types of USB. You have the micro, the mini, and those. What we want is USB type B. Okay, all right. So we bring that here. Now let us connect it up. Okay, so the USB has four main signals. If you have actually opened up your USB cable before, you see four main signals. Okay, there is two for power, that is the V bus and ground, and the power for the USB is usually 5 volts. Is that okay? Then we have two for the signals, which that's what we have. That's what labeled D plus and D minus over here. Okay, so let's connect this up. Now, this V bus here is a means of powering up our system by using power from the computer. Is that okay? So that means that we can get power from this V bus. Now, two things that we can do. Two things that we can do. For now, we can just probably choose to connect this directly to our 5 volts since it is also a 5 volts. Okay, you can do this. However, if you do this, you risk your computer. Okay, why am I saying that? If anything goes wrong, if anything goes wrong, let's say I have connected an external voltage, but unfortunately my 7805 is faulty. And so instead of 5 volt, probably it's something happened and I'm getting 6 volt over here. That means that now current is going to flow into your computer. I don't know what blocking mechanisms they have over there, but I'm not ready to take those chances. Is that okay? But then we already know how to cause current to flow in just one direction, right? Who can remind us of that? How can we restrict current to flow in just one direction?
Use of diode.
We use a diode. We use a diode. So instead of doing this direct connection here, okay, instead of doing this direct connection, we will bring this diode, and again, we need a Schottky diode because if you use any regular junction, PN junction diode, the normal ones, they have a forward voltage drop of what? About 0.7, right? So that means your incoming 5 volt will end up as a 4.3 volt, which is not ideal. However, we know that this Schottky diode should do right about 0.3. So even if we have an output of 4.7, it is quite manageable. Is that okay? So you make sure, and in fact, even if you could set for a diode with a better forward voltage drop than this, I think it will be superb. That would be ideal. But for now, let's just say we are stuck with the Schottky diode. So now if I connect this Schottky diode here, then I could connect its output to my 5 volt supply. Now, by doing this, something interesting has also happened. Okay. One thing I don't remember the first scenario that I said. Let's say I connected an external VCC and then something happened. This voltage breaks down. Is that okay? And instead of 5 volt, it is producing 6 volt. You see, that means that this point will go because this 5 volt is attached to the output of the 7805. If it generates 6 volts, then it is going to put 6 volts over here. And what will happen if I have 6 volts here and 5 volts here? What will happen? Assuming our 5 volts regulator is faulty, so it generates 6 volts, right? That means this will not be 5 volts anymore, it's going to be 6 volts. We know that the USB bus, the V bus, is producing 5 volts, okay? So what will happen if I have 6 volts here and 5 volts here? What is going to happen? Yes, any takers?
Yeah, I think it will be now forward biased.
Check it well.
So
Check it well. So something
it's
happened. Instead of 5 volts
reverse.
here, we are getting 6.
Okay,
Uh-huh.
okay. So it's supposed to be reverse biased, but the voltage will be higher. So I think the breakdown voltage will be exceeded, or I think the depletion voltage or something. The barriers will be exceeded.
Okay, so you were very close. Okay, Christine, yes, you can chip in. Christine,
It, it will overlay.
where the overlay means, there is just this single term I'm looking for. Okay, so maybe let me take it again. Okay, we are supposed to get 5 volts here, right? But then something has happened. This is actually producing 6 volts now. But this V bus is also producing 5 volts at this point. Okay, this point is producing 5 volts. So what will happen if I have 5 volts here but 6 volts at this point? What will happen? Yeah, Kojo Ewusi.
It will blow the fuse.
Kojo Ewusi, it won't blow the fuse, okay? All right, Joshua,
Okay.
what's it now?
The dad will be reversed biased.
Fantastic. That is it. Okay. Remember, I said that reverse biasing a diode simply means that the potential at the cathode should be higher than the potential at the anode. And where is the cathode? Remember, we said the diode symbol shows the flow. Okay. You can see that the arrow goes this way. That means that this is the anode, this is the cathode. So if we have 6 volts at the cathode and 5 volts at the anode, it means that the diode is reverse biased. That means that whatever current is coming from this V bus will be blocked. Is that okay? So in a way, this diode has protected our V bus. Now, let's even assume that everything is working fine. We have plugged in our USB cable and we have also plugged in our external power supply, right? So what is going to happen is that this voltage regulator is going to take the external power supply and generate 5 volts out of it. In that case, we would have two voltage levels, something coming from the USB and something coming from the power supply. But the diode is actually doing something interesting here. Who can tell me what is actually happening? When I connect an external power supply, what would happen to the power coming from the V bus? Uh-huh. Your network or something, I can't really hear. The diode would what? I can't hear you. Yes, any
It will
other
still
any
block.
come again?
It will still reverse and block the current flowing
Exactly.
from there.
You see, the fact of the matter is that if we have the same voltage here and there, the system is still shut down. Is that okay? Remember, for the diode to be forward biased, there has to be what? A potential gradient, the voltage difference. And the voltage difference has to be such that the anode has to be higher than what? The cathode. So if I have 5 here and 5 there, this diode will still block whatever current is coming from the V bus. Is that okay? So this is a very simple way of doing voltage selection. But then, if you look at Arduino schematic, they actually did something different. They used an op amp and some, comparators and stuff. Okay, I'll still do that with you. I'll still do that with you so that you can check it out. Okay, I'll still do that so you can see how that one also works. So let's finish routing this up. Let's finish routing this. So connect this, connect that. Now in PCB design, we call something differential pair. Okay, differential pair. Now D plus and D minus are differential pair. God willing, when we start talking about PCB, I'll talk about what differential pair is and explain more. Okay, but because they are differential pair, you see, we don't have our IC here in the meantime, so we are going to label this connection. Okay, we're going to label this connection. Later, I'll show you. I'll tell you something about this labeling. Now, whenever certain signals are differential pair in KeyCard, you have to give them the same name, but then you have to put a plus or minus on them. Okay, so the D signal, the D plus, I'll do D plus and put it there like that. So I've labeled it. Then I'll do the next one, D minus. Okay, so this plus and minus actually are serving a purpose. They are not just for naming sake. Is that okay? They are not just there for naming sake. They will come in handy when we start to route this signal as a differential pair. Okay. All right. Now let's finish up with the connector. Now we have two pins left to connect. We have the ground, which we could just hook up to the ground like that. Now let me put in some distance. I'm going to talk about something. Now, what we have here, this pin 5 is connected to the shield. Usually, if you open a USB cable, you realize that there is this shield around it. Okay, it's a metallic shield. Is that okay? This is supposed to deal with something called EMC, EMI, and blah 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 stuff, right? Good. And usually that shield connects to the body of the USB. Okay. Now, usually how I deal with this, since it could pick some signal noise in there, what I do is hook it up to a very small capacitor, usually 1 nanofarad, and then connect it to the ground, the PCB ground. That is what I do, and actually, that's what some mentors of mine recommend. Okay, so uh, I never place the components. I'm looking for C small. Okay, so here I need 1 nanofarad. Okay, so I'll connect the shield. I'll connect the shield through this 1 nanofarad, then to the PCB ground. Okay. Now this 1 nanofarad is supposed to deal with shunt any high signal noise that will be picked by the cable, or that will be inside the shell. Okay. So from here I could connect that. Uh, Let me just bypass this guy. Okay, put this here and there. Okay, so we are done with the connection for the USB. And again, what I'm going to do is drag this down and bring a header to it. Again, this is not necessary. It is something that I like to do. So call it USB B ports. Let's just call it that. Again, this is not a requirement. It is just something I do. All right. Okay. So now let's also look at the other way of performing the voltage selection. Okay. There is there is a there is a component called a comparator. Should I actually talk about this? Should I actually talk about this or just leave it like this? I'm confused because if you want to go then okay, I haven't talked about opams. Opams are not simple stuff. Okay, should I talk about it or not talk about it? Who wants me to talk about it? Yes, Emmanuel Ajeni. Yes.
Sir, please, where from the D plus and the D minus?
Okay, so they are just labels. So just take it as I have named these lines. Okay, this net, I've named them.
Okay.
Okay, yeah. You will see their use
Okay.
later, but for now, just take it as I've named them. Is that okay?
All right. Okay. Thanks.
Yeah. So I'm still contemplating on whether to show the Arduino way of power selection or we should just leave our power selection in there and continue. What do you guys think? Yes, what do you guys think? Should I do the Arduino way too? Because I actually don't see, unless there is something special about that, I think. So, are we okay with this, or I should also demonstrate the Arduino way of doing stuff?
Also demonstrate the Arduino way
I should
too.
demonstrate. Okay, so how much will you bribe me? All right. Okay. So if you look on the Arduino board, they also have a way of doing it using a comparator. Okay. Now, before I talk about that, let me probably explain what a comparator does. So a comparator is an IC, a special type of op-amp, operational amplifiers. That's the reason I didn't want to talk about them. They're a special type of operational amplifiers. Now, what they do is, as their name implies, they compare two voltages and select one or perform an action based on something. Okay, they select that is basically their function. So let's see if we can get any comparator. I think LM33. Yeah, LM quad. No, I don't want a quad. I want just a single one. LM334. No, 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 no. LM33. Okay, let's just go online and pick a comparator. Or let me see, I've actually used one before. Let me check the part number and then we just use that. Okay, it's quite interesting. It's quite interesting, but yeah, I'll do it. I'll do it. What am I looking for? Data sheets. Yeah, any questions? I'm finding looking for something. If you have any question, please. Okay, that would be power. Yes, please. The sound, the text sound, is it directed to me? Because like I said, I'm not checking our power. So if you are sending text messages, can I get okay, somebody gave that. Oh, okay. Thank you. You guys are doing why we use Schottky diode instead of normal diode in input. Where is the high frequency in input? You use Schottky diode. Is Ahmed still here? Ahmed, is Ahmed still here? Okay. Please, if Ahmed is still here, Ahmed, you can still read it. Okay. So, Ahmed, you said, why are we using the Schottky diode instead of, because we are not dealing with any high frequency, okay? Are you talking about the V bus or are you talking about the V bus or you are talking about this side? Okay, so probably let me just explain the two quickly. Now, I'm using Schottky diode over here. Now, if you look at the other diodes like the 1N4001 series, right? I think the maximum current they can handle is about 1 amp. Is that okay? And usually, if a component has, let's say, a maximum current rating of 1 amp, you don't want to be driving it at that 1 amp. Okay. Looking at our system, this particular voltage regulator here could actually deal with 1.5 amps. And so in case, and even this fuse is limiting everything to 1 amp. Okay, so I just don't want a situation where the diode would have to take so much stress. Okay, now if you look at this Schottky diode, it can actually deal with 3 amps. It also have a small forward voltage drop, which is actually something I'm still counting on. Now, the voltage drop, looking at what we are doing, wouldn't have been an issue, but except for the amperage. Is that okay? So here, this is not considered because of any high frequency stuff. It's just because of the amperage, because this guy can handle about 3 amps. So that means drawing 1 amp through it wouldn't even cause it to heat up and all that kind of thing. And it's the same thing. In fact, over here, actually, this is too much for this line because we are using USB 2.0, and USB 2.0 can actually give, I think, a maximum of about 500 milliamps. So later on, I'm going to search and see if there is any Schottky diode that can do about 1,000 milliamps. I'll replace this with that. Yeah. Okay. So we're going to also look at how Arduino implements their thing, right? Okay, so I think the IC I'm looking for is LM331. The LM334 is a quad, but I just want a single. Okay, so let's look for LM331. No LM331. Oh, LMV33, LMV 331. Yes, good. So you can see that it's a comparator, a single general purpose low voltage comparator. Okay, and I'm counting on its low voltage. So let's put this comparator here. Okay, now just a little about this comparator. What the comparator does is it has these two inputs. Okay, the inverted and non-inverted. Let's call it a V plus and V minus, right? And it has an output that it can switch. So we're going to connect this pin 2 and pin 5 to certain voltage levels, and depending on which of these input voltages is high, the output would be one of these voltages that we're going to put in. Okay, so maybe let me just start designing and then you can appreciate it. Okay, so the voltage level I want to deal with would be 5 volts. So I'll put 5 volts here. And the other one I want to be selecting would be ground. So let me put ground here. Okay. So 5 volt there and then ground over there. Now let's connect them up over there and okay. Now this is our output. We will drive something with our output, but for now, let's finish with the comparator. Okay. Now, we now have to connect the voltage that we want to compare. Okay, the voltage that we want to compare. Fortunately, what we have to be driving would have to be a transistor, and specifically a MOSFET transistor. You see, the reason I didn't want to touch this, a lot of stuff that I haven't talked about will end up coming into the scene, and I don't know how most of you are going to take it, okay? But there is something called a MOSFET transistor. A typical example that I usually use for this operation is, I think, FDN 3 something, 340, yeah, 340p. Now, this is a P-channel MOSFET. For the sake of time, I cannot explain what these things are about, right? So just appreciate the general idea of the whole thing, okay? Just appreciate the general idea of the whole thing. Now, let's go and check out this transistor, okay? So FDN 340p. If we go online and search for FDN340P. FDN340P. Okay, so it's produced by On Semiconductors. Let's check its data sheets. Okay, so you can see that this is the type, the package. We will look at this when we start PCB design. But this is the label. We have the gate, the drain, and the source. Okay, gate, drain, and source. And the gate is actually pin 1, the source is pin 2, and the drain is pin 3. Now, if you come to our circuits, so gate is pin 1, source is pin 2, and drain is pin 3, right? But you see, this is a P MOSFET. Is that okay? This is a P MOSFET. We need a negative gate to source voltage to cause it to work, to switch on, or yes, we need, in order to switch it on, okay, there's a transistor, so it serves as a switch, okay. So in order to switch it on, we actually need the voltage drop between the voltage between these two pins to be negative, okay. So what I'm going to do is I'll right click on this. Usually I want my sources to be up, higher potentials up and lower potentials down. So I will mirror this vertically so that now the source is up, okay. Now the source is up and the drain is down, okay. So if I need the VGS, we call it the VGS, okay, the gate to source to be negative, then that means that, look at something, if I hook this guy to 5 volts, if I hook this guy to 5 volts over here, and then for now, let me just put this net at this point, okay. I need you to follow me. I know a lot of these components you are not familiar, that's why I didn't want to touch on this, okay, but follow me. Now look at something. How can we get a negative voltage to drop between these 2 points if we have 5 volts here? Okay, you see, if this comparator switches, sorry, this comparator, when it turns on, right, it will select 5 volts. That means it will output close to 5 volts at this point. Okay, so let's say it's able to put exactly 5 volts over here. That means we are going to get 0 volts, which is actually not very ideal. Is that okay? So technically this should turn off. Okay, VGS is going to be like 0, which should put this P in an off state. Now off state means that current cannot move from here, from the source to the drain. Okay, current cannot move from the source to the drain. Now source to drain, because we are dealing with what, a P MOSFET. But then when it switches to this, when it switches to ground, right, when this signal, and I'm going to show you what will lead to the switching. When it switches to ground, that means there will be 0 volts here. And that means that VGS is going to be 0 volts minus 5 volts, which will give us what, minus 5 volts. And that is going to cause this transistor P MOSFET to turn on. Turning on means now current can now flow from this 5 volt to whatever we connect here. Okay. Now, how do we perform the selection? Now, we want to actually detect whether VCC has been connected or not. Is that okay? We want to detect whether VCC has been connected or not. So what I'll do is, I'll bring VCC down here. And when VCC is connected, I want this to select a 0 volt instead of the 5 volt. So I'll connect the VCC on the inverting input. Okay. Now, I'm going to do some voltage splitting using resistors. And again, for those who are very new to these things, you won't understand it, but please pardon me. God willing, tomorrow when I talk in depth about resistors, you would appreciate what we are doing. Okay, so I'm going to put these 2 volt resistors here and use it to create a potential divider. Okay, going to use it to create a potential divider. Now, all that this potential divider, let me actually stretch this out and put this guy to here and bring this in the middle. Actually not in the middle. All right, so I'll connect this to that, this to here, to here, to that, and then ground this point. So from here to this point. This is the reason I don't want to touch on this. It's quite complex. Okay, so let's put this here and ground this. But I'll try my best to explain it so that you guys can understand. Okay, and then connect this to the junction between the two resistors. Now, I want this, one more thing, one more thing. I'm simply going to hook up this positive signal to the 3 volt output, like that. I'm going to hook it directly to 3 volts, okay? So that will be a fixed signal on this positive voltage. So look at what will happen. Whenever there is no external voltage connected, that means I haven't plugged in the power from a battery or any other source, right? But just only the USB power is powering up the Arduino. That means that I'm going to get 0 volts at this point, okay, because VCC will be 0, so I'll still have 0 volt at this point. In that case, between 3 volt and 0 volt, this 3 volt will be higher, and higher means that the output of the comparator is going to switch to 5 volts. Now, what do we already know? When it switches to 5 volt, then we will get VGS to be 0, which will actually not cause this P MOSFET to turn on. That means that, okay, that means that this 5 volts here would be conducting, or will not be conducting. What happens? I think I've actually inverted. Okay, so when I connect this, I want my 5 volt to turn off instead. Oh, sorry. I've actually interchanged the signals, I guess. Okay. So rather, when I want, when I connect my, this quick one. Okay, let me put this guy just here. Delete this. So please just pay attention, okay? Listen to the tells myself. Usually these things confuses me. So I'm going to take it over again. This is what I'm trying to achieve. Whenever I connect an external power supply, the system should stop taking power from the USB. That's all we are trying to achieve here. Okay? When we connect an external power supply, the system should no more depend on the USB for power. That's what we are trying to do. Okay? So this is how this system will select between this 5 volt or ground, the comparator. When the voltage on V1 is higher than the voltage on, when the voltage on pin 1 is higher than the voltage on pin 3, it will select the 5 volt. That means it will output 5 volts here. When the voltage on pin 3 is higher than the voltage on pin 1, it is going to select this. So it's going to put ground, which is also 0 volt over here. That's the simple mechanism, right? So let's look at a scenario where we don't actually, a scenario where we haven't connected this to any power source, right? VCC is 0. Now, when VCC is 0, this is what's going to happen. This negative line on pin 3 would have a higher voltage than pin 1, right? And we know that when pin 3 has a higher voltage than pin 1, the output is going to be ground. So that means ground will be established here. When we have ground established here, then what is going to happen is that we are going to get a negative voltage drop between the gate and the source, which will cause current to flow this way. Now, actually, the voltage we need here is V bus, not 5 volts. So let me adjust this guys here. And please take note, if you are doing, you should always do just one of them. Don't do the two, okay? Just implement only one of the cases. So I'm going to put a label at this point and call it V bus. V bus, okay? So V bus is the voltage, the 5 volt coming from the computer. Now we are trying to either use it or not use it, okay? So I'll copy this, and look, in KeyCard and in all other software for designing circuit, anytime any node or any label, any net is labeled the same way, any two nets are labeled the same way, it means they are connected. So technically, this means that I have connected a wire from here. I've connected a wire from here all the way to here, right? But you see, doing that will be very messy. So the other way or more efficient way of doing it is to put the same labels on them. So when you see V bus anywhere, it means that that particular thing is connected to this point. Please, is it okay? Fantastic. So when there is no power here, as we have already seen, that means the voltage on the inversion on pin 3 is going to be higher than pin 1. That means that this would output ground. When this output grounds, we are going to have 0 volts versus the V bus, which is actually also 5 volts, and that's going to give us a negative voltage drop, a negative voltage across the gate and source, which is actually what we need to turn on this MOSFET. So when that happens, now current can flow from here to our 5 volt. That means our system will now be powered by the USB. The system will now be powered by the USB. But then when we connect VCC, now let's choose this resistors. Let's choose this resistor. Now, and in this particular situation, I don't actually care about the current, but I need just a little amount of current. In fact, something in the micro amp region, okay, very tiny. But what I need is I need the voltage that will build up across here to be higher than this 3.3 volts, right? So I can probably establish, let's say, 5 volts here or 4 volts here, okay? Something higher than this 3.3 volts, right? So let's try to drop a 4 volts here. How do we choose resistors so that we can drop a 4 volts here? But here we have to be careful too, because if the person connects 7 volts, okay, the person connects 7 volts, and you divide 7 into 2, that will give you 3.5. Well, 3.5 is still higher than 3 volts, so technically it should work. Okay, so we have to choose this resistors very carefully. Okay, you have to choose this resistors very, very carefully. All right, for now, this is what I'm going to do. I'm going to adjust the such that it can divide, but I'll have to cross check whether I can put a higher voltage than what is on the V plus and V minus, okay? But for now, let's assume we can do that. So I'm going to choose a very high resistance for this, let's say 100K. This is to ensure that very little amount of current is flowing. Technically, this is an open current is not supposed to flow. But then, of course, that's an ideal situation. Then I'll choose another 100K over here. Okay, so choosing 100K just means that it is always we are always going to have a voltage at this point higher than this so far as this is connected. Is that okay? Because to use the VCC, you actually need to connect something from 7 volts upwards. So if we do that, then we're going to have a voltage drop here. So let's say VCC is 9 volts. When VCC is 9 volts, this resistor, these two resistors will divide the 9 volts so that we have just 4.5 volts over here. Now, because we have 4.5 volts over here and 4.5 is higher than this 3.3 volt, what do you think will happen? This is going to switch to, the output is going to switch to 5 volts. When it switches to 5 volts, then we are going to get a positive voltage or 0 here, which will cause this transistor to switch off. Now, when this transistor switches off, it means that we are no more taking power from the V bus, but now the power that we'll be using in our circuits would be coming from the voltage regulator, which is in turn taking its power from the VCC. And that is how you do the selection. That is how I think it's implemented on the Arduino. Yes. Please, any questions? If you are confused anywhere, don't worry. I'm still. I'll just go over it. I never intended touching on this, but some of you wanted it, so because I haven't talked about a lot of things on there. Yeah, please, any questions? Any questions? Any questions? Uh, Give me a moment. It's raining at my end. Let me just get some things out of the rain. Okay, just a moment, please.
Oh, please, I have a question. Prof, which question?
He will be back.
Okay.
All right, please. Any questions? Any questions? Any questions? Any questions? Now, the next session we are actually going to.
Hello, sir.
Yeah.
Uh, please, sorry for taking us back small, but I wanted to ask, what the difference between a surge protector and a fuse? Because that thing is baffling my mind small.
Oh, okay. Can somebody help him? Can somebody help him? He's asking the difference between a surge protector, something like a TVS. Actually, I'll be connecting a TVS in this work, but for now, just yeah. Any ideas? If you can answer him, please answer. I don't want to be the
Yeah, I'm
only person.
listening.
Okay. Yeah. Okay. Yeah. Can anyone answer him? He's asking what's the difference between a surge protector and a fuse. Yeah, Joel, go ahead.
Sir, please, the question again. I should ask the question again.
He said the difference between a surge protector and a fuse.
Uh-huh.
Any ideas? Any ideas? Yes. Okay, the one who has the question, what do you know fuses are used for?
Um, please, I'm the one who asked the question.
Oh,
Joel.
okay. So if nobody is taking it, let me, or somebody wants to. Okay, so you see, a surge protector, okay, usually is supposed to flatten out spikes, okay? When we say
Okay.
surges, take surges as some temporarily or transient voltage spikes in circuits, okay? sometimes,
Okay.
for instance, if you have lightning outside, it could lead to surges. If you have noise somewhere in around your circuit or whatever you are doing, and you are dealing with sensitive signals, it can cause some spikes. Okay, and these spikes are usually in the form of voltage rise. So a surge
Okay.
protector is supposed to flatten out these spikes. It doesn't
Okay.
necessarily shut down the system, right? But a fuse
Uh,
is like a fuse way of working it. It checks for overcurrent. So
uh,
surge protectors is actually dealing with voltage spikes, but fuse is dealing with overcurrent. And for a fuse, I mean, when the current exceeds its recommendation, it has to break down and then disconnect your system and make sure it is safe. Okay. But surge
okay.
protectors are always there actively doing their work without shutting down your system. Okay. But the
Okay.
main
Okay.
difference is that surge protectors are usually flattening or smoothing out spikes. We call them voltage spike.
Okay.
So that's it. Yeah.
Okay.
Please, any other question or any other idea? Yeah.
Thank you, sir.
Christine, yes.
I am not sure if I'm the only one who didn't get it, but you were to give the differential pairs meaning, the D positive and the D negative.
Yes, yes. Okay, so the reason for this labeling would be very clear when we start doing the PCB. Okay, it's just a convention used in KeyCard so that KeyCard can see that this has to be handled as a differential pair. Okay, so when we start routing, I would go over that again, and you would see why we did that.
Okay.
Is that okay? Yes. So for now, just assume that I've just labeled these signals D plus and D minus. Okay. All right. Please, Joel, your hands is up.
Sorry, sir. My question is being answered.
Oh, okay, okay, okay. Please, any other question? We have just a few minutes to end this session. Let's use it for discussion questions, whatever you need. Yeah. Yes, please. Any questions? Any questions? Any questions? By the way, we have to decide which of this we are using. Okay. Yeah, Christine, go ahead.
You said, was it a fixed or a variable capacitor that its values can't be changed?
Can't be changed. That's fixed.
And okay, and variable can be changed.
Exactly. So your the vote in a radio, what you use to change the stations, right? In a
Yes.
radio, yeah, that's an example of a variable capacitor.
Okay.
Yeah.
Prof, please, I have a question.
Okay.
Please, why is it that the other diagram you didn't bring a fuse there?
Which other diagram?
Please, the one like the one that has the triangle there.
This one.
Please, no, the one on the right side.
Okay, here.
Please, yes,
Your question is why didn't we do what?
bring a fuse there.
Okay, so we only need a fuse at one point in our circuit, okay? And that is where the power is coming in. Are you okay? We don't need to be putting fuses at different places. No. We only need the fuse here. The power coming from the USB, that one we don't have to worry about because the computer is regulating that already. So we can trust it. Is that okay? We can trust it. All right. Joshua Tete, yes.
Yeah, Mr. Bean.
Yes, sir.
Yeah, I wanted to clarify something.
Okay, okay.
Yeah, you mentioned that the surge protector flattens out voltage spikes,
The
and the surge protector,
okay.
you said it flattens out voltage spikes.
Okay.
So I want to know if that means our capacitor we have in there is a surge protector.
Oh, okay. All right. So there are actually special components called is it TVS, right? Transient voltage protectors. Okay. There are special things for that. Okay. How do I even put this? How do I put this? How do I put this? How do I put it? You see, the spikes we are talking about can be actually very high. Okay, these spikes that we are talking about. In fact, let me probably bring something. Okay, I don't have it. When we use the capacitors, we are usually looking at, in a way, yes, we are filtering those, we are trying to shunt or absorb those high frequency signals, right? Those signals may not necessarily be spikes, they could be something that is coming continuously. Like, you see, the spike is supposed to be a transient kind of thing, something that is not happening continuously, but like it happens once a while and then it's not actually needed. I don't know if it is making any sense. But when we for the capacitor thing, the spikes we are talking about is usually part of the signal, okay? But the transients, they usually just come from nowhere, they superimpose themselves and cause our voltage to spike or rise temporarily. Okay, so uh and
Okay, so
usually, where I'm coming, where we
okay,
put these things, you can't actually put capacitors there. For instance, we are supposed to put transient TVS over here. If you put a capacitor here, you would distort your signal. Okay, because this signal is supposed to be changing. Okay, 0 1 0 1 0 1 is supposed to be changing, and we know that capacitors don't allow what change in voltage. Do you get it? So,
yes sir.
and in this situation, if we want to deal with transients or even this kind of uncalled for spike, we can't use a capacitor in this session, but a TVS can be used here ideally. Okay,
Okay,
but
so
I'll really look at. In fact, you've drawn my attention to something. I'll check it out probably tomorrow. I'll see if I get anything different on it. Okay.
okay. So Mr. Bin, you are saying the TVS just absorbs the extra voltage
It's
we are
not like
getting.
absorb. Okay, they kind of the way they operate is like when the extra voltage comes. Yes, we can say they absorb, but they shunt it. When we say you are shunting something, it's like they redirect its effect,
Okay,
so
okay,
that it doesn't affect our circuit. Something
okay,
like that. Yeah.
okay. Thank you very much, sir.
You're welcome. Yeah, Christine. Yes.
Is it only the type B USB port used by Arduino, or you can use the other type A also?
Actually, we are designing our own board, so wherever we want to use, we can use. Okay, just that we want to create something similar to the Arduino, so that's why we are using that. But if we want, let's say USB Mini, USB Micro, or Type C, we can use it.
Okay.
Yeah. Please, a few minutes to stop. I think I will end this session here. When we come back, we are going to do the connection for the actual microcontroller. Okay, that's why I don't want to continue. So let's use this to answer questions. If you have anything on your mind, and please, the senior men in the house, you are also welcome to answer some of the questions.
Prof, please have a question.
Okay.
Please, so the triangle thing is part of the USB port.
Come again.
Please, is the triangular thing part of the USB port?
No, no, no. So this thing is this triangular thing, okay? It's called a comparator, okay? Say
Yes,
comparator.
comparator.
Exactly. So what it is doing is it's comparing these two voltages, okay? It's comparing these two
Yes.
voltages. Now, if the one that is bigger, so let's say if the one that the voltage on pin 1 is higher than the voltage on pin 3, it will output 5 volts here. If the voltage on pin 3 is higher than voltage on pin 1, it will output ground over here. Okay, so it's a comparator. Now, it is not part of the USB. Okay, it's not part of the USB.
It's okay.
All right.
It's okay, please. Thank you.
Please, more questions. All right, Ajenim Boateng, please, you can go ahead and ask a question.
Sir, please, the other diagram that is being connected to the comparator. What's the name given to it?
You mean this one?
Yeah,
It's called a
that
MOSFET,
one.
a P MOSFET.
Okay.
It's called a
But
P MOSFET.
what is the purpose of it? What's the purpose of it?
So take it as a switch, okay? Take it as a switch.
Okay.
You know what a switch is, right? Now, we want,
Yeah.
when we switch it on, power will move from this V bus to our 5 volts. Is that okay?
Okay.
And the way, you see,
Okay.
in the switch in your house, you have to manually press it on or off. But the way we
Yeah.
are pressing this on or off is by supplying either 5 volts or 0 volts to this point, pin 1. Is that okay? When we
Okay.
supply 0 volts, it will turn on. When we supply 5 volts, it will turn off.
Okay.
Yes.
All right. Thank you.
You're welcome.
Please, and the other one, the triangular one.
Comparator.
Comparator. Okay, the comparator.
Yeah.
It is the same as a voltage divider or.
No, it's not a voltage divider. What we have done here is a voltage divider. Now, tomorrow morning, I'm going to talk about voltage divider, so don't miss it, okay?
All right. Okay. Thank you.
You're welcome. Yeah, so we're still designing. We are yet to touch on the IC itself. I think that is the last part for today. Yes, the last part of today, we'll be touching on the IC. I'm very happy to do that. Yeah, please, more questions, else we will be done here in the next 5 minutes. Yes, more questions. Yeah, Gilbert.
So, let me just ask.
Okay.
Something. Let me just ask this. So, what happens if the inputs on the comparator are equal?
I have no idea.
assuming you supply 6 volts,
Yes.
and then
Yes,
you divide
I think that's a
divide.
good question. That's a good question, but I have no idea. I'll check it out. I have never thought of that. Anyone with any idea? Anyone with an idea?
I think that
It's
I
not.
think it will be reversed.
It's not a matter of thinking. No, this we are working with facts. If anybody has any idea on it, please. Yeah, Gilbert, please go ahead.
Oh, okay. My question was coming with the comparator.
Okay.
Okay, can you hear me?
Yes, I can hear you.
Okay. With the comparator,
yeah,
there is the VCC which we supply, and then there's the other one, the 3 volts.
Here.
You say that we use them to like determine which one to be like whether we switch it on or switch it off.
Exactly. So you see we want this one. Go on.
Okay, my question is coming here now. The 3 volts there, it means that it doesn't serve any purpose in the circuit, and it doesn't flow in there. It just works there like as a like the switch on button, and the VCC, when it's disconnected, that's when now the 3 volts act as the switch on, but when it's connected, then it back comes as the
exactly. So whenever we connect VCC, right, it means that we're going to we get a higher voltage here more than this, then this is going to switch off the USB. That means that the system, the Arduino, will not be taking power from the USB. Okay, so the moment we take off our external voltage, then this automatically switches back to 3 volts, right? And then the Arduino, the USB is switched on so that the Arduino is powered by the VCC, yes. Sorry, powered by the VBus, which is the voltage from the USB. So something like that is happening. But we could also achieve that same thing using this simple mechanism. Okay, so
Yes.
these are just like two ways of doing the same thing. I'm yet to know. Probably, I know definitely the engineers at Arduino knew that something like this exists, but probably there is a reason why they did this. I'm yet to find out.
Okay.
Yeah,
Okay. Thanks a lot.
you're welcome. Okay, I have idea in OPAMs, and I think I can help with that. Okay, James. James Dazi. I think if you can answer that question. I think the question was what happens when pin one and pin three are the same, right? So okay, so Enoch, if you have an idea, please turn on and explain it to them. Oh, technically, wait, technically, a comparator is supposed to, when you configure OPAMP as a comparator, it's supposed to amplify, is it the voltage difference? OPAMPs amplify voltage difference or something? I have to check. Yeah, Enoch, if you have an idea, please answer in. Yes, any other questions? Any other questions?
Well, please, I have a question.
Okay.
Please, the J and D, does it mean ground?
Yes, GND means ground.
Okay, please, thank you.
Hello.
Yes.
Hello.
Yeah, James, you can talk.
And based on the, let me say, the configuration of that circuit,
Okay.
you can say that it has been configured in op amps. We have something that we call differential, like differential. Um, it's just like,
Differential
let me say,
mode, right?
yeah, and it operates in, let me say, it get the difference in the voltages,
Mm-hmm.
like a subtractor or something like that. Yeah.
Okay.
So when there's a difference between where we have the positive um, three 3 volts, that plus 3 V3 or something like that,
Yeah.
and it compares it with where the VCC is,
Mm-hmm.
and based on the gain that has been like given to or already been done to what the op amps or
Yeah.
that component,
Yeah.
based on the gain that it has, then it will be able to amplify that voltage
Okay.
and set it as an output to the next circuit.
Okay. Okay.
So like that's my idea in it.
Okay. But now you see, there is still a fundamental question unanswered. If the voltages are the same, right?
Yeah.
And that means the difference is going to be zero. Now, if you amplify zero, it's still gonna be zero, right?
Yeah.
So
Yes.
that means then it's going to select which one.
Okay. Looking at the circuit,
Mm-hmm.
let me check. Okay, we have an input to be zero, and if the input is zero, the input is zero. That's for our own. We say, let me say V1. That's
Mm-hmm.
the input.
Yeah.
It's zero, meaning that the output has to be what, zero too. So if the output is zero, meaning that whatever is going to the next circuit has to be what, zero.
Okay.
Has to be zero. So on that on that alone, you can say that there will be no output from let me say to that device. So
Okay. So even
it
if
will
the
start
output is
taking
zero, right? Even if
uh-huh
the output is a zero, that means it's ground. It's technically
yeah,
going to be something like ground. So
ground,
then
yeah,
this should switch on, right? The
yes,
USB would have to would take over. In fact, this is a
yes.
very interesting question. I've never analyzed it that way before. That's good. That's good. I'll check more on it. Probably this comparator. Sometimes I don't know. Some of them could have some offset potential or some minimum threshold. I'll check. I'll check up on the comparator and see if there is something like that. Then
Okay.
yeah. So remind me tomorrow, God will, and we'll look at it. Okay. All right, Christine. Please answer your question.
I was trying to answer what you were saying, whether the if both inputs are of the same
Okay.
value,
Okay.
despite it being used to check if an input has reached some predetermined value,
Mm-hmm.
I'm not so sure if it can happen to be so, because every every input voltage an offset has an offset voltage. Wait, I'm contradicting myself. They can't be the same because they're all different.
Okay. But you see, the potential divider we are using here, okay, divides our voltage exactly into two. So that means if I put in a voltage of 6.6 volts at VCC, do you get what is happening here? If I put 6.6 volts here per this voltage divider configuration, I have to get 3.3 here. So if that happens, then we have 3.3, 3.3 here, right? So that's what we are trying to find out what is going to be if these voltages are the same. Okay. If I had a simulator, we'd have probably checked it out. But don't worry, don't worry. I will find out more on this IC and then yeah, if
Okay.
there is anything. All right, I
Hello, sir.
think
Mr. Obin.
yes.
I'm a bit confused now.
Eh,
The comparator,
okay.
does it amplify the difference between the inputs, or it selects one of whether 5 volts or ground based
Okay,
on
so
which of them?
please, it compares the input and switch. For now, just take it like that, okay? So that I don't get super confused again, okay?
Okay.
Just take it like that, okay? So it
Okay.
will check this too because when it is switching between these two values. Is that okay? Switching between these two values. So for now, just take it as if whichever is higher, it selects the associated voltage. Okay, so don't confuse yourself with
Can I
any
come in?
more detail. Yes, 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 Adam.
Okay, so since we said it's a voltage selector, right?
Okay.
So if they are equal, it's definitely going to select one.
Exactly.
Yes, so even if they are equal, it will select one because those are the only options it has,
Of
right?
course,
Yeah,
yeah,
so
of
I think
course.
if they are equal, it will select one.
I think this afternoon session has been interesting. Yes, yes, we are rounding up. We are rounding up. Yeah, any more questions? Any more questions? We are rounding up. So in the third section for today, I think we let me check the list what we are supposed to do. So in the first section, actually we started doing a part of the test section, placing USB connector. Okay, so in the test section for today, we would actually we just finished the test section. Comparator, transistor. Ah, oh, okay. Okay, so no worries. I still have something to make up for. So in the next session that we're going to do, we're actually going to connect the IC itself and route the components about it. Okay, then as we are doing, I'm going to explain what the components are doing and some of the other stuff that needs to be known. Okay, Gilbert, yes, go ahead. Ajeni Mboaten and
Well,
Gilbert, yeah.
well, just saw something on the comparator.
Okay, okay.
There's somewhere where you say that the PCP voltage it never goes below the 7 volts.
I can't really hear you well.
Oh, the VCC voltage
Uh huh.
said that it cannot go below 7 volts.
Yes, but it can be off, right?
Oh, okay.
Okay, so you mean no? But you see, the thing is, you don't know what somebody will do with the system, right? Probably the person has a 9 volt battery, but it is low in voltage, and let's say it's at 6.6 volts.
Mm,
You get it? It's a possibility. But the thing is, you have to defend your system against any unforeseen circumstances. LMV 331. I would have to look into. I never actually paid much attention to it. Yeah. Any other question? Please, is your question answered? Are you okay?
Yes, 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 I'm okay.
Okay.
hello.
Yes. Please go ahead.
So please, can you look at the USB port?
Okay.
There is a place. There is a place that has been named Shield.
Yes.
Yeah, what, what's it doing there?
Okay. So the shield is
Sorry.
the shield refers to the metallic case. Okay. And if you
Okay.
if you look at if you have ever stripped open a USB cable, you see that there is this metal net around it. Mhm. That net is
Okay.
not just there for beauty sake. So if your USB cable doesn't have that, please throw it away. Okay.
Okay.
Yes, if your USB cable doesn't have that, please throw it away. That net is there to shield the signals from surrounding noise. Okay, so it also connects to the
Uh,
metallic part of the USB cable. That's the shield. Is that okay? So just take it as the
okay.
metal part of the USB cable. That's the shield.
Okay. All right. Thank you.
Okay. I think if we have, once we answer the question, let's play the TVS diode. So TVS, I think I have one in my library. DS, that. Let's use ESDA. Yeah, this is what I usually use. This is what I usually use in my work. So this is a transient voltage suppressor, TVS. So usually it's a good idea to put TVS on these lines, okay, the USB lines. But you don't know where the cable is coming from, how good the cable is, and all that. So I'll connect pin 1 to that, pin 2, actually, let me go the other way around. Pin 1 to V bus, to that, and then to that. Now in keycard, when you have an IC and there is a particular pin that you will not connect, you have to let keycard know that you have intentionally left that thing empty, else it will complain. Okay, and the way you let keycard know is by placing this cross on it. We call it no connection. Okay, so by putting this no connection, I'm telling keycard that I know that these pins are not supposed to be connected, so be okay with it. Okay, something like that. All right, then we connect this to it. So now we've connected our transient voltage suppressor. Okay, so we are technically okay with the USB ports. We are okay with the USB port. Okay. All right, Kojo, we see your last question, and probably I'll take one more question, then we break and return in the next 1 hour, 30 minutes. Yeah. So 30 minutes, 5 o'clock. So our next class is at 6. Okay. So we are going to eat fast because that is when we are going to do the real deal. So don't miss it. Okay. Any more questions, please? Any more questions? Any more questions? Any more questions? All right. So if no question, then thank you for joining the second session. I'm going to again send a snapshot of what we've done, where we've gotten to so far on the page. Okay, so if you have been routing along, you could do that before the next session start. Now, in the next session, we are going to first design the library for the AtMega 328 IC. Okay, you take the data sheet, go through the data sheet, and then use the data sheet as a guide to design a library. You associate a footprint for the library, and then you will now bring it to do some routing. Okay. All right. Thank you very much, and see you at 6 p.m. GMT.